Hi guys, this is Mr. Robeson. We're here today to talk about experiment design. So we've got a couple more techniques in experiment design to go over, like placebo, the placebo effect, factors and levels, blocking, match pairs, and blinding. So first of all, what's a placebo? So a placebo is a treatment that has no active ingredient, but is otherwise just like the other treatments. So it's no active ingredients. Oftentimes this is like a fake pill, or we call it a sugar pill sometimes. All right, so it's used with experiments when people are taking drugs or pills often. So we don't want them to know if they're getting the actual drug or if they're just getting a regular old, just some candy basically. All right, and the reason we do this is because something called the placebo effect. So some subjects in an experiment will respond favorably to any treatment, even an inactive one. So if we give them the fake one, some of them are going to feel better no matter what. So they're going to be happy, they're going to feel better, even if it's a fake pill, just because someone's telling them, here you go, take this, it'll make you feel better. And that will make them feel better. So here's an example. In a drug trial, participants are randomly assigned to two groups. One group is given an active drug, and the other is given a placebo, so an inactive drug. It's not really a drug. After 1 day, participants are asked if they feel better. For the drug group, 60% felt better. For the placebo group, 30% felt better. All right, so some people are going to feel better just on their own. Some people are going to feel better just because the act of doing anything. So this is why we always want to be able to compare drug trials to a placebo to see if that drug is actually having the effect or just the act of taking something is having the effect. So in this case, 60% is a lot bigger than 30%. So it looks like the drug's probably helping. But if this was 30% and the drug group was 35%, or also 30%, then we'd say, you know what, this drug is just not working. All right, the next thing I want to talk about is factors and levels. So when we're talking about our treatments or explanatory variable, a factor is a specific part of the explanatory variable, and a level is a different degree of each factor. So factors are broken down into levels, explanatory variables are broken down into factors. So we went over this in class a little bit. So like if we're cooking a cake, one factor could be the temperature, and the level could be the different temperatures, like 300 degrees or 350 degrees or 400 degrees. And like we could say the different amount of sugar would be levels for the factor sugar, the different amount of flour would be levels for the factor flour, the number of eggs we'd use would be different levels for the factor eggs. All right, now this brings us a new definition for treatment, or kind of an evolved definition of treatment. It's a grouping of different factors with their different levels that is assigned to the subject of an experiment. So for instance, our cake is to be made, but we don't want to know what we want to use for the best recipe. One recipe calls for cooking it at 300 degrees, another calls for 350 degrees, and a third calls for 400 degrees. One recipe calls for half a cup of sugar, another one says to use a full cup of sugar. One recipe, you should say one. One recipe says to use 1 egg, another recipe says to use 2 eggs. There's 3 different possible treatments. So a treatment is a collection of these factors at their different levels. So a treatment here, we'll call it treatment 1, would be 300 degrees, half cup of sugar, and I'm just choosing the first one here, 1 egg. That would be a treatment, all of those together. Another treatment would be any other collection of those factors. So treatment 2 would be, say, 350 degrees. We could still go with half a cup. We could also go with a full cup, it doesn't matter. And we could go with 2 eggs, or we could go with 1 egg. As long as one thing is changed, that's another treatment. And it says list 3, so another one. Treatment 3. Let's go back to 300 degrees. This time let's use 1 cup of sugar, and let's use 1 egg. All right, so there's another treatment. All right, so any collection of these we want to put together, we can do that. So now, how many different treatments are there? Well, we had 3 options for the first, we had 2 options for the second, and we have 2 options for the third. So we just multiply together. So 3 for the first times 2 for the second times 2 for the third is 12. So this was 3 temps. So the factor was temperature, 3 levels. This was sugar. All right, we had half cup or a full cup. We had the 300, 350, and 400. And then for this last one was eggs. The factor here was eggs. The levels were 1 and 2. All right. So if we just multiply those together, we get 12 total possible treatments. It's a lot of cakes you're going to have to make, guys. So if someone's going to have to make 12 cakes, I will do the taste testing, okay? I'm here for you guys. Blocking. All right, so blocking is when we take a grouping of experimental units that are known before the experiment to be similar in some way, and that way could affect the response to the treatments. So men and women is often blocks. So usually we'll have men in a block and women in a block, especially in drug trials, because men and women both, they often react differently to different drugs. All right, the reason we do this is to try and reduce bias, because maybe men will react one way and women will act another way. All right, so here's another example. So a farmer has an outdoor garden and an indoor garden, like a greenhouse, where he grows tomatoes. He would like to know if using a specific type of fertilizer will cause the tomatoes to grow larger. How would he use blocking to test the fertilizer? All right, so he could say we'll use the fertilizer only on the indoor and just keep doing what he's doing on the outdoor ones. But then we don't know if it's the fertilizer that's causing him to grow better tomatoes or if just the indoor greenhouse is just a better place to grow tomatoes. So what we do is we use blocks. So we've got outdoor and we've got indoor. And then within each of these, let's go ahead and put boxes around them, we're going to do basically their own separate experiment. So we're going to give half the fertilizer and half normal. And the same here, we're going to have half of the indoor ones get the fertilizer and half of them just the normal way we would grow the tomatoes. And then after this, we would compare these results. And same here, we would compare the results within the indoor. So we were not comparing indoor to outdoor, we'll compare indoor to indoor, we'll compare outdoor to outdoor. It's basically like saying instead of doing one experiment, we're going to do two smaller experiments. All right? And these two smaller experiments are going to eliminate bias because these guys are all going to be similar in one way because they're all indoors. And these guys are all going to be outdoors. And these guys are all going to be similar in one way because they're all indoors. So we're doing this to reduce bias. All right, a very specific type of blocking is what we call match pairs. So instead of blocks, it's actually just pairs. So two very similar experimental units are paired, very similar like maybe identical twins. And two treatments are normally randomly assigned in each pair. So like one of them will get treatment A, the other one will get treatment B. Or each experimental unit receives both treatments in a random order. So like you'll do A first and then you'll do B second. Or you do something with your right hand, then you do something with your left hand. All right, and again, this is to control for outside variables, often called confounding variables, but extra variables that could creep in. This is why we want them to be as similar as possible. This is why we like doing studies on twins. Twins. All right, so here's our example. In multiple sets of identical twins, we find a bunch of identical twins. Don't ask me where we find them. We just find them. One twin is assigned to eat a vegan diet, the other twin to eat a non-vegan diet. The weight loss is compared at the end of 3 months. All right, so now if we're testing a diet, we want the subjects to be as similar as possible to see if the actual diet plan is what's causing them to have a weight loss, the vegan versus non-vegan diet. There's our explanatory variable. Or if there's something else, like maybe some people are just motivated to lose weight more than others. Who knows? All right, but that's why we want it to be as close as possible. That's why match pairs is always a good design if we can get it, but it's not always the easiest thing to do. All right, and the last thing here, blinding. So blinding is when somebody doesn't know what they're doing. All right, so single blind, either the subjects don't know which treatment they are receiving or the people who interact with them don't know. Usually it's the subjects. The subjects generally don't know. All right, or the person that's measuring the response variable. So generally, like the single blind one is the taste test. Right? They're almost always done blind because we don't want the person to see what they're taste testing. Right? Or we'll just pour Coke into one cup, Pepsi into the other cup, and if you can't tell the difference, then we don't need the blindfold. But otherwise, a blindfold works perfectly well for blinding. All right, so subjects don't know which one they're trying, And they're just going to try each one and say, oh, the first one, A, tastes better. Or, oh, B tastes better, the second one. Right? That's single blind. Double blind is when neither the subject nor those who interact with them and measure the response variable know which treatment the subject receives. So the doctors won't know and the patient won't know who's getting the actual drug and who's getting the placebo, the inactive drug. All right, and this is done to reduce bias. So we're going to try and reduce bias. Some people they know they like Coke better than Pepsi, but if we give them a taste test and they don't know which one's which, then they can't just say, oh, I like Coke better. All right, here again, it's to try and reduce this bias, because if a doctor knows they're getting the drug, he might be more likely to, tilt the numbers in a certain way. So what we do is somebody in the background knows which drug they got, but not the doctor who talks with the patient. All right, so that is double blinds. It's really easy just not to tell the patient which one they're getting. We always just tell them they're getting the drug. All right, so that is experiment design part 2. Check the Google Classroom for the assignment for this one.